Picture this. You are the chief risk officer of a massive global bank. Or maybe you are the group tax director of this sprawling multinational corporation.
Right. Highly stressful jobs, even on a good day.
Oh, absolutely. Yep. And you are sitting in a very quiet, very tense boardroom. Across the mahogany table is a federal auditor. Or maybe a chief regulator.
The pleasantries are definitely over at this point.
Yeah, they are long over. They slide a single piece of paper across the desk. On it is this gargantuan multi-billion-dollar figure.
Right.
It's either a capital requirement that dictates how much cash your bank has to lock in a vault, or a colossal global minimum tax bill.
Which can completely tank a quarter.
Exactly. So they look you dead in the eye, they point to that massive number, and they simply ask, prove that number.
And that is the exact moment where the oxygen just completely leaves the room.
I can imagine.
Because in modern finance, despite all the processing power we have, proving that final aggregated number in any sort of rigorous, mathematically undeniable way, it's a near impossibility.
Really? Even with all the tech they have?
Yeah, you can show them your spreadsheets, sure, and you can show them your models. But proving the unbroken chain from the raw data to that final digit, the infrastructure simply hasn't existed to do it.
Which is terrifying. And that terrifying boardroom moment is exactly what we are plunging into for this deep dive. We are looking at a solution to this specific nightmare.
And it is a fascinating solution.
It really is. It's an institutional RegTech platform, regulatory technology called OrbaOS FRTB GloBE, built by a company called Rondanini.
Right, Rondanini.
And the architecture is just wild. It features two self-hosted calculators sitting on top of one shared cryptographic engine. One calculator handles FRTB, which is market risk capital for banks.
Yeah.
And the other handles GloBE, which is the OECD's Pillar Two global minimum tax for multinationals.
It's wild because you have two entirely different regulatory regimes here. One deals with the trading desk, market volatility, risk models, right?
Right.
And the other deals with international tax treaties, local trial balances, corporate subsidiaries.
Totally different worlds.
Completely. Yet from an architectural standpoint, the people running these departments are suffering from the exact same structural disease. The data just gets lost in translation.
So our mission today is to explore how cryptographic principles, things like Merkle trees, which you might normally associate with blockchain or digital currency, are being ripped out of the crypto world and deployed to solve massive existential compliance headaches in traditional finance.
It really is an entire paradigm shift in how financial governance operates.
Okay, let's unpack this. Before we can appreciate the sheer mechanical elegance of the OrbaOS solution, we really need to understand the agonizing reality of what these institutions are facing right now.
We have to understand the multi-billion-dollar headache.
Yeah, the reconciliation problem.
Right. To grasp the scale of the reconciliation problem, you really have to look at how drastically the regulatory landscape shifted post-2008.
After the crash.
Exactly. After the global financial crisis, regulators woke up to the fact that the models banks were using to calculate their risk were incredibly opaque.
They were just black boxes.
Total black boxes. So the Basel Committee introduced FRTB, the Fundamental Review of the Trading Book. It was this total overhaul of the rules dictating how much capital a bank must hold in reserve against the risk that, their trading portfolios might just blow up.
And it isn't just a slight tweak to the old rules, right? It's a massive overhaul that forces banks to calculate risk at this incredibly granular level, running thousands of different market shock scenarios.
Thousands. It requires immense computational horsepower. And concurrently, over in the corporate tax world, the OECD introduced Pillar Two, commonly known as GloBE.
The global anti-base erosion rules.
Right, GloBE. This mandates a 15% global minimum tax on large multinational enterprises. The goal is to stop that race to the bottom, where a massive corporation parks all its intellectual property in some zero tax haven to avoid paying taxes where it actually does its business.
Sense.
But both FRTB and GloBE represent regulatory undertakings of staggering scale. You are pulling millions of rows of data, piping them through labyrinthine rule sets, and spitting out a final number that literally determines your legal compliance.
And if you ask a layperson what the hardest part of complying with FRTB or GloBE is, I think the knee-jerk assumption is that the math itself must be the bottleneck.
Oh, absolutely.
Because you look at FRTB regulations, and it is a wall of stochastic calculus, Greek letters, complex probability distributions. You look at GloBE, and it's this tangled web of sovereign tax treaties.
It looks impossible.
But that assumption that the math is the hard part, That's completely wrong.
Is the defining misconception of the financial industry.
Really?
Yeah. The math is a known quantity. The regulatory formulas are published in black and white. Banks employ armies of PhD quants, and multinationals have entire floors dedicated to Big Four tax accountants.
Right. They know how to do the math.
They know how to run a stochastic model. They know how to calculate an effective tax rate.
So we have to state the core truth right up front. Most FRTB programs don't fail on the math. They fail on reconciliation.
Yes. Let's trace the operational failure mode because it is universally messy.
Okay, lay it out for us.
Imagine a major bank trying to comply with FRTB. The risk department extracts a massive file of sensitivities. This is raw data showing how much their portfolio's value changes if, say, the Japanese yen ticks up 0.5% or European interest rates drop.
Got it.
They take that file and they upload it to a shared network drive.
A shared drive. Already I can feel the anxiety building.
Oh, it gets worse. The finance department takes that file. An analyst opens it, maybe spots a few rows they think are erroneous outliers, deletes them manually, and feeds the rest into a calculation engine.
Manually deleting rows. Okay.
Right. So the engine runs overnight. The next morning, the audit team takes the output, drops it into a massive Excel spreadsheet, adds some manual overlays based on a late-breaking regulatory interpretation, and produces a final capital figure.
And let me guess. The final number doesn't match the original expectations, and the totals do not tie.
They never tie.
Never.
Never. The risk system's preliminary estimate says the capital should be X, the finance engine says Y, and the final regulatory filing in Excel says Z.
What a mess.
So when the regulator in that tense boardroom asks, prove that number, nobody can definitively trace back from the final multi-billion-dollar digit to the original data.
Because there's no paper trail.
None. If there's a discrepancy, nobody can say which specific input byte broke the reconciliation. Was it the analyst who deleted the rows? Was it a parameter change in the engine? Was it a broken Excel macro?
But what does the auditor actually get?
The auditor gets handed a messy folder of random CSV exports, disconnected spreadsheets, and disjointed SQL queries.
It's like trying to trace a single drop of water in a downstream bucket back to the exact cloud it rained from.
That's a great way to look at it.
Yeah, I mean, once it hits the river, once the data shifts from risk to finance to audit to Excel, its origin story is just gone. You can't separate your one drop from the rest of the water without a tracking mechanism.
The water analogy is evocative, but it implies a natural blending. In financial data, it's actually more insidious. It's not just blending, it's unrecorded mutation.
Oh, I see.
And this disaster isn't confined to banking. Look at a multinational group dealing with the GloBE minimum tax. You have a parent company in London with 40 subsidiaries scattered from Dublin to Singapore.
Yep.
You have local accountants producing local trial balances and local accounting software. Then the central tax team in London applies what they call Article 3.2 income adjustments. Then a Big Four accounting firm does an independent recompute in their own proprietary software to verify it.
So you have 3 different sets of hands mutating the data across 3 different geographic locations and software environments.
Exactly. Instantly, the numbers drift. A local accountant in Dublin adjusts a depreciation schedule on a Friday afternoon. A tax reviewer in New York overrides a covered tax inclusion on Monday morning.
And nobody knows.
Right. By the time the final GloBE information return, the GIR XML file is generated and submitted to the tax authorities, it is an orphan. It is completely disconnected from its source rows.
Wow.
The corporation is essentially saying to the government, trust us, we did a massive amount of work to get this number, but they lack the mathematical ability to replay the journey.
Which is an existential risk when a rounding error or dropped spreadsheet row isn't just a typo, but a $50 million capital shortfall or a massive tax penalty.
Precisely.
So this brings us to the architecture of OrbaOS and how they approached this systemic failure. They essentially looked at the legacy workflow, which is calculate first, try to reconcile the mess later, and they inverted it. They introduced a philosophy called the Admissibility Doctrine.
Yes. Admitted before calculated, that's the whole product.
Let's repeat that soundbite, because everything else we talk about is built on top of it. Admitted before calculated.
In a legacy system, the engine is hungry. It will swallow whatever CSV or spreadsheet you feed it, run the math, and spit out a number.
Right.
OrbaOS operates on the principle that a number cannot even enter the calculation engine until its provenance, its exact cryptographic identity and origin, is mathematically locked into place.
It's a gatekeeper.
Exactly. They enforce a strict chain of custody from the very first byte of raw data all the way to the final export handed to the regulator.
But how does a system actually lock a number? I mean, if I'm an analyst staring at a screen, I'm just looking at rows and columns. How do you turn a spreadsheet cell into a cryptographic lock?
It's a very rigid process.
Yeah, the OrbaOS documentation outlines this beautiful, ruthless 6-step flow. Let's walk through the mechanics. Step 1 is parse and canonicalize. What does canonicalization actually mean in this context?
Canonicalization is about stripping away formatting ambiguity. When a risk analyst uploads a CSV file of sensitivities, the OrbaOS system doesn't just blindly accept it.
Oh.
It parses it and forces it into one strictly defined, standardized format. It validates every single row against a pre-agreed schema contract.
Give me an example of how ambiguity sneaks in if you don't canonicalize.
Dates and currencies are classic culprits. One system might export a date as month, day, year, another as year, month, day.
Oh, that happens all the time.
Right. Or one analyst might upload a value as just 100, assuming the system knows it means thousands of US dollars.
Yeah.
The OrbaOS schema contract refuses that. A numeric field must explicitly declare its unit. It must be 100,000 USD. It forces the raw data into a pristine JSON payload where there is only one possible interpretation.
Got it.
And once the data is canonicalized, the system generates a SHA-256 hash of that payload.
Let's pause on the SHA-256 hash because people hear that and immediately think of Bitcoin. But it's a fundamental computer science tool.
Yeah.
It's essentially a unique digital fingerprint for a piece of data. Right.
Exactly. It's a deterministic cryptographic function. You feed it a payload, and it returns a fixed-length string of alphanumeric characters.
Okay.
What makes it powerful is the avalanche effect. If you take a million-row spreadsheet and generate a hash, you get a specific fingerprint. If you go into row 500,000 and change a single comma to a period, the hash doesn't just change slightly.
It changes completely.
It changes completely and unpredictably. The hash is an absolute guarantee of the payload's exact byte-for-byte state. So the system canonicalizes the data, generates this fingerprint, and hands the fingerprint back to the analyst's software.
Which leads to step 2, the hash echo commit.
Yeah.
The system has shown the analyst the fingerprint. Now, the caller, the analyst system, must echo that exact hash back to OrbaOS verbatim. It's like a cryptographic handshake. The analyst is effectively signing a receipt saying, I acknowledge that this is the unalterable fingerprint of the data I am submitting.
It is a critical legal and mechanical threshold. If the hash they echo back doesn't match what the system generated, OrbaOS flatly refuses the payload.
Okay, here is where I want to push back, because I'm thinking about human behavior. Let's say I'm that analyst. I upload my massive CSV. The system gives me the hash. I'm just about to hit confirm and echo it back.
Okay.
But in that split second, I realize I made a mistake on one line. I open the CSV on my desktop, change a 9 to an 8, save it, and then echo back the original hash I was given to save time.
Ah, I see where you're going.
Because in a legacy system, that data just overwrites quietly. What does OrbaOS do?
It rejects the commit immediately.
Instantly.
The moment you change that 9 to an 8, the intrinsic identity of your file changed. The file you are now trying to commit generates a brand new SHA-256 hash on the server side.
Oh, because the backend recalculates it.
Exactly. So when you echo back the old hash, the system sees the mismatch. It throws an HTTP 409 conflict error.
So it literally locks you out.
It locks you out, but more importantly, it generates an inadmissibility event. It writes a permanent record saying, this specific user tried to commit data, but the cryptographic provenance was broken. It prevents silent drift.
Silent drift. That one change cell that goes unnoticed ripples through a million calculations and ends up skewing the final capital requirement by $50 million.
Yeah.
Catching that at the front door is massive.
It really is.
So we've parsed the data, we've echoed the hash, the data is admitted. Now we move to step 3, Merkle DAG construction. You mentioned Merkle trees earlier. How do they actually structure this data?
A Merkle-directed acyclic graph, or DAG, is a way of structuring data so that every piece is cryptographically chained to the pieces that came before it.
Okay.
Picture an inverted tray. At the very bottom, you have your leaves. In the OrbaOS system, these leaves are the hashes of the individual canonicalized rows of your input data.
So leaf 1 is the hash of row 1. Leaf 2 is the hash of row 2.
Right. Those input leaves feed upward into a function node. The function node represents the actual calculation engine, for instance, the FRTB Standardized Approach engine.
Gotcha.
But this node isn't just a generic label. It is mathematically bound. It contains the hash of the specific version of the calculation software being used, the hash of the specific regulatory regime parameters applied, and the hashes of all those input leaves beneath it.
Oh, wow. So it's not just saying we ran the calculation. It's saying we ran version 2.1 of the calculation using the UK-specific parameters on this exact set of immutable input rows.
Precisely. The engine executes the math and produces an output. That output is then hashed together with the function node beneath it to form the output root, the root of the tree, the final multi-billion-dollar number.
And the beauty of the Merkle DAG is the absolute dependency.
Yes.
If you change one input leaf at the bottom, the hash of that leaf changes, which changes the hash of the function node, which changes the output root hash.
Everything cascades.
Yeah, if a developer secretly updates the calculation engine from version 2.1 to 2.2, the function node hash changes and the root hash changes. The final number is mathematically bolted to its history.
It creates a state of mathematical unforgeability, which brings us to the fourth step, exporting. Because eventually, the bank has to hand this number to an auditor in a format they can read, like an Excel workbook.
Right.
When OrbaOS generates that export, it includes a dedicated provenance sheet. This isn't just a summary. It explicitly lists the final root hash, the specific function reference that produced it, and the hashes of every single input leaf row.
Wait, what if someone tries to run an export report on data that bypassed that strict hash echo commit step?
Yeah.
Let's say someone just force-fed a table into the database to get around the system.
The renderer simply refuses to generate the export.
It won't even output the file.
No. If the system cannot trace a perfect, unbroken cryptographic line from the output back to an admitted input, it will not allow that unproven number to leave the environment. It fails closed.
Okay, but put yourself in the auditor's shoes for a second. They get handed an Excel file. The first sheet has the capital number. The second sheet is this provenance tab filled with hundreds of SHA 256 alphanumeric hashes.
Right.
To a human, that just looks like digital gibberish.
Yeah.
How does an auditor actually know they aren't just looking at random strings of text generated to placate them?
That is the most critical hurdle, and it's solved by the stateless verifier. OrbaOS provides a standalone offline Python script called verify_lineage.py.
Oh.
The auditor takes the lineage JSON file provided alongside the export, puts it on their own disconnected laptop, and runs that script.
So they don't even need to be connected to the bank's network or the internet.
No network access required. They don't need to log into the bank's backend, and they certainly don't need to trust OrbaOS as a vendor.
Oh, that's huge.
It is. The Python script takes the raw input data provided, walks up the Merkle DAG, and recalculates every single hash from the bottom leaves to the top root. If the script's recomputed root hash perfectly matches the root hash printed on the report, the auditor has mathematical proof that the number is untampered.
They only have to trust the laws of mathematics.
Exactly. It fundamentally removes the trust me element from financial audits.
And I was reading the documentation on this verifier, and it is aggressive. It specifically hunts for 5 strict failure modes. It doesn't just throw a generic error message. It pinpoints exactly how and where the chain of evidence was shattered.
It's incredibly precise.
Walk us through these 5 modes because they read like a catalog of every dirty trick or innocent mistake in accounting.
They map perfectly to the realities of data drift. The first failure mode the verifier catches is hash mismatch. This is the most direct form of tampering.
Like changing a number on purpose.
Right. If someone opens the raw payload after it was admitted and changes a single byte, maybe they alter a currency value to make the risk look smaller, the verifier flags it immediately. And it doesn't just say the root is wrong. Because of the DAG structure, it isolates the exact localized node where the tampering occurred.
It points directly to the exact row that was altered.
Yes.
So that's direct tampering. What's the second failure mode?
Edge leaf mismatch. In graph theory, the edges are the connections between nodes. This failure occurs if a function node, the calculation, claims it was produced using a specific set of input leaves, but the actual connections in the graph point to a different set of leaves.
Wait, give me a real-world scenario for that.
Imagine a scenario where a capital number is finalized, but later an auditor asks to see the underlying data. The team realizes the original data had an embarrassing error, so they quickly swap out the original input file for a corrected one.
Hoping the auditor won't notice.
Exactly, hoping they won't notice that the new data doesn't mathematically result in the old output. The verifier catches the mismatch between the claimed leaves and the actual edges. You cannot retroactively swap the foundation of the house after the roof is built.
Which leads to the third mode, which sounds similar but happens higher up the tree. Edge function mismatch.
This happens when the final output root points downward to a function node that is simply missing from the graph entirely.
Okay.
The system demands a continuous, unbroken chain. If an output claims to come from a specific calculation, but that calculation's cryptographic identity isn't present in the connecting edges, the verifier rejects it. The documentation refers to this as preventing silent reparenting.
I see. So I can't take a final capital number that I really like and artificially attach it to a completely different calculation process to make it look legitimate.
Exactly.
It's like claiming I baked a cake from scratch, but the receipt in my pocket shows I bought it from a bakery. The provenance has to match the output.
That's a perfect analogy.
Now, the fourth failure mode is the one that I think is the most insidious in legacy finance: function reference drift.
Without question, this is the hardest error to catch in traditional systems. This occurs when the input data is perfectly untouched, but the parameters of the calculation secretly change.
Like tweaking the dial on a machine when no one is looking.
Exactly. A quant might go into the model and slightly update a volatility scalar to make a portfolio look less risky, or perhaps a regulatory parameter silently shifts from the EU calibration to the UK calibration without a formal version update.
And legacy systems miss that.
Legacy systems often don't track these parameter shifts cleanly, but the OrbaOS verifier catches it instantly because the function node's hash is fundamentally bound to the specific engine version and the parameter set.
So if the auditor expects version 1.4, but the node claims it used 1.5, the chain breaks.
Silent parameter changes are impossible.
That locks the model's exact state in amber. You can't quietly tune the math. And the fifth and final failure mode.
Root not nut deset. This is the simplest. The Lineage payload claims a final root hash exists, but that hash doesn't actually exist anywhere in the proven graph of nodes.
It's an orphan root.
Exactly. It's a number that someone just typed into a cell, materializing out of thin air with no mathematical history. The verifier refuses it entirely.
And the system doesn't just wait for these errors to happen. The documentation notes that the stateless verifier has 76 automated tests running constantly, actively bombarding the system with deliberately tampered data to prove that it catches these exact 5 errors every single time.
It's a level of rigor that makes traditional spreadsheet auditing look like guesswork.
So now that we understand the absolute strictness of the admissibility doctrine, let's look at how it applies to the specific complex domains it was built for. Let's start with the Bank Chief Risk Officer and dive into the FRTB modules.
Right. FRTB, as we noted, is about market risk capital. The regulators demand to know how much cash you need to survive a sudden market shock. OrbaOS divides this computation into the 2 primary regulatory approaches: the standardized approach, or SA, and the internal models approach, IMA.
Let's start with the standardized approach. It sounds simple, but the math is incredibly dense. The engine computes SBM, DRC, and RRAO.
Yeah, lots of acronyms.
For someone who doesn't spend their life in risk management, what are we actually calculating?
The standardized approach is designed as a universal baseline by regulators, so they can compare risk across different banks using the same yardstick. SBM is the sensitivity-based method.
Okay.
The OrbaOS engine takes the bank's sensitivities, meaning how much money do we lose if equity prices drop 10% or if the yield curve shifts. It applies prescribed regulatory scaling factors to these sensitivities. Then it aggregates these risks.
And it aggregates them in a very specific order.
Yeah.
Right?
Yes. First, it aggregates within specific buckets, for example, comparing tech stocks to other tech stocks. Then it calculates correlations across different buckets.
Right.
Next is the DRC, the default risk charge. This calculates the jump to default risk. What happens to our capital if the sovereign nation or the massive corporation we are trading with simply goes bankrupt overnight?
Nice.
Finally, RRAO is the residual risk add-on. It's a regulatory catch-all for highly exotic trades or complex risks that aren't fully captured by the SBM or DRC formulas.
Got it.
The OrbaOS SA engine computes all of this inline, and it binds every single scaling factor and correlation assumption into that Merkle DAG we discussed.
So that's the baseline. But if a bank's trading operation is sophisticated enough, they don't want to use the generic standardized approach. They want to use their own models, which brings us to the internal models approach, or IMA.
IMA is where banks use their proprietary risk models, which can result in lower capital requirements, but only if they meet incredibly strict regulatory hurdles. IMA is vastly more computationally intensive.
I can imagine.
The OrbaOS pipeline handles expected shortfall, or ES. This is a measure of extreme tail risk, essentially calculating what happens in the absolute worst 2.5% of market scenarios.
And doing that isn't just running one calculation, it's running it across different time frames, right? Because you can't sell a complex derivative as fast as you can sell a share of Apple stock.
Precisely. That's called multi-liquidity horizon aggregation. The system recognizes that some assets take 10 days to liquidate in a crisis, while others might take over 100 days.
Wow.
OrbaOS calculates the risk across those different horizons. It also computes the IMCC, the default risk, and handles some of the most brutally complex rules in FRTB, RNT, and NMRF.
Okay, let's unpack those acronyms because they sound like a compliance nightmare. RFET and NMRF. What happens when a risk can't be modeled?
RFET stands for risk factors passing the eligibility test, and NMRF stands for non-modelable risk factors. Imagine a bank is holding a highly customized derivative that has only traded twice in the global market over the last year. You do not have enough observable historical market data to feed into a statistical model to predict how that derivative will behave in a crisis.
So what does the regulator say to that?
The regulator says, you can't model this cleanly, so we are going to penalize you for the uncertainty. The bank has to identify these non-modelable risk factors, separate them from the modelable ones, and apply a stressed expected shortfall, or SES, calculation to them.
That sounds like a mess to track.
It is a data tracking nightmare to prove to a regulator exactly which factors were modeled and which were penalized. By pulling all of this into the Merkle DAG, OrbaOS provides instant proof of exactly how every single risk factor was classified and calculated.
That is a staggering amount of math. But doing the math is only half the battle. You have to hand the result to a specific regulator in a specific country, and they all want it formatted differently.
And this is where the alignment of the platform is crucial. A bank operating in the UK has to report its capital numbers to the PRA, the Prudential Regulation Authority, using very specific templates like SS2115.
Right.
If they operate in the EU, they report to the EBA using COREP templates, specifically C90, 91, and 92. In Australia, it's the APRA APS 116 template.
So how does OrbaOS handle that jurisdictional translation without breaking the cryptographic chain?
OrbaOS natively maps its cryptographic outputs directly into these rigid regulatory templates. The specific regime parameters, whether you are applying Basel 3.1 default rules or a specific regional variation mandated by the PRA, are hard-coded and mathematically bound into the function node's hash.
That's smart.
The regulator gets the exact visual form they demand, but it is backed by a cryptographic guarantee.
I want to shift our focus for a second to what the chief risk officer actually experiences when they use this software. We've talked deeply about hashes, DAGs, and stateless verifiers, which sounds like interacting with the back end of the matrix.
Right, very abstract.
But inside the product UI, the experience is translated for the executive.
That's vital. A CRO is not logging in to look at JSON payloads. When they open OrbaOS, they start at the dashboard. They see a clean, stacked bar chart showing their total capital requirement broken down instantly by SBM, DRC, and RRAO, segmented by asset class.
So it looks like normal software.
It looks like standard enterprise software. With one click, they can export that data to Excel, PDF, or directly to those EBA or PRA templates.
But if they want to dig deeper, if they want to see the proof, they click over to the Lineage tab, and this is where the cryptography becomes visual.
On the Lineage tab, they actually see a visual representation of the Merkle DAG. They can trace the flow of data from the input leaves at the bottom through the specific calculation function node all the way to the output root at the top.
Oh, that's cool.
Every single node displays its SHA-256 hash. It takes the abstract concept of cryptography and turns it into tangible visual evidence.
There is also a scenarios module that caught my eye because it comes preloaded with historical crisis presets. Why is that so important for a CRO?
Stress testing. Regulators constantly want to know what happens to your bank if history repeats itself. The Scenarios module allows the CRO to take their perfectly proven baseline data and instantly subject it to historical shocks.
Like what kind of shocks?
They can ask, what would our capital requirement look like if the 2008 global financial crisis happened tomorrow? Or the 2011 Eurozone debt crisis? The 2020 COVID shock? Or the 2022 UK LDI crisis?
Wow.
They can run the engine against those parameters and see the impact immediately with absolute confidence that the underlying baseline data hasn't drifted.
And finally, there's the firm module, which handles the difference between diversified and naive aggregation. Explain how those two concepts differ when calculating risk for an entire bank.
Well, a global bank has many different trading desks. Desk A might be trading equities in London, while Desk B is trading foreign exchange in Tokyo. If you calculate the risk of each desk completely independently and just add all those numbers together, that's naive aggregation.
Okay.
It assumes the worst-case scenario happens everywhere simultaneously. But in reality, risks often offset each other.
Right. If desk A is heavily long on the US dollar and desk B is heavily short on the US dollar, the firm as a whole isn't exposed to the dollar moving because the positions cancel each other out.
Exactly. Diversified aggregation pools all the sensitivities across the entire firm, runs the calculation engine once across that unified portfolio, and surfaces the diversification benefit.
Showing the savings.
It shows the bank exactly how much capital they save because their internal risks hedge each other.
Right.
But regulators are inherently skeptical of diversification benefits. They will scrutinize that netting calculation fiercely. Because of the admissibility doctrine, the auditor can perfectly trust that firm-wide netting calculation because every underlying sensitivity is cryptographically anchored.
It fundamentally transforms how a risk department defends its numbers. But the sheer brilliance of the OrbaOS platform is that this exact same cryptographic engine, this same philosophy of admitted before calculated, is simultaneously solving an entirely different, equally massive problem in the corporate tax world.
The GloBE tax rules, yeah.
So if you think tracking market volatility is a headache, imagine trying to apply this exact same cryptographic lock to international tax law, where the rules change depending on what country the money flows through.
Let's enter the GloBE labyrinth.
The GloBE labyrinth.
Mhm.
OECD Pillar Two, the 15% global minimum tax. It is, without exaggeration, the most significant rewrite of international corporate taxation in a century.
It's massive.
And it's incredibly complex because it applies retrospectively across multiple jurisdictions. I used the analogy of a cascading waterfall earlier to describe how the tax money is routed. And I want to refine that because the mechanics are fascinating. But before we get to the waterfall where the tax is collected, we have to look at how OrbaOS traces the water to the river.
Right, the article walks.
The system traces every financial step through the specific articles of the GloBE model rules. Break down these article walks for us. Where does the data start?
It begins with the raw constituent entity inputs, the local financial data from every subsidiary in the multinational group. The first crucial step the system enforces is the Article 3.2 walk.
What does that do?
This is where the local book profit, what the subsidiary reported on its local audited financial statements, is systematically adjusted to become what the OECD defines as GloBE income.
Because what counts as profit in local accounting might not count as profit under the new global rules.
Exactly. The OECD rules mandate very specific adjustments. OrbaOS enforces an 8-line item walk per entity to bridge that gap. It's not a black box calculation, it's a visible bridge. Every single adjustment is hashed and tracked into the Merkle DAG.
So we figure out the real GloBE income.
Yeah.
Then what? We have to figure out how much tax they already paid, right?
That is the Article 4.1 walk. It bridges the book tax, what the local statements say was paid, to what the OECD defines as adjusted cover taxes.
Okay.
This is a 4-line item walk. Again, every line is visible. If a central tax director overrides a local tax inclusion, that override is explicitly marked, hashed, and bound into the tree.
So now we have the GloBE income and we have the adjusted cover tax. We divide them to find the effective tax rate. But before we actually calculate if they owe top-up tax, there are the Article 9 safe harbors.
Right, the safe harbors.
This is basically where companies pray they get a pass so they don't have to do the full calculation.
The safe harbors are a regulatory relief valve. They are designed to reduce the immense compliance burden for operations in relatively high-tax or low-risk jurisdictions. OrbaOS mathematically evaluates 3 OR tests per jurisdiction.
What are the 3 tests?
First, the de minimis test. Does the jurisdiction have less than 10 million euros in revenue and less than 1 million euros in profit?
Okay, pretty straightforward.
Second, the simplified ETR test. Does their simplified effective tax rate meet a year-indexed threshold, which is transitioning up to 15%? And third, the routine profits test. Is their profit less than their substance-based income exclusion?
What does that mean in plain English?
Meaning, is their profit mostly driven by actual physical payroll and tangible assets in that country rather than just intellectual property parked in a shell company?
Ah, I see. And if a jurisdiction passes any one of those 3 tests?
They short-circuit to 0 top-up tax, the engine flags it, hashes the result, and moves on. The jurisdiction is safe for that year. And crucially, the system tracks the once out, always out rules across multiple years.
Okay, but what if they fail the safe harbors? What if they are operating in a low-tax jurisdiction and their effective tax rate, their ETR, is definitively below 15%?
Then the top-up tax applies.
This is where the routing logic comes in. This is the waterfall. And we need to go into extensive detail here because this is where the geopolitical complexity truly explodes. The group owes money to bring the tax up to 15%. Which country gets to collect it?
The OECD recognized that deciding who gets the money would cause chaos, so they created 3 collection mechanisms, and they apply in a strict hierarchical order.
Bucket 1 of the waterfall. The first right to collect, the QDMTT.
QDMTT stands for Qualified Domestic Minimum Top-Up Tax. The rule here is geographically logical. The source jurisdiction, the country where the low-tax profits were actually generated, gets the first right to collect the tax.
Makes sense.
If that source country has enacted a domestic minimum tax that the OECD officially recognizes as qualified, they collect the full top-up locally.
So let's run a hypothetical. A multinational has a subsidiary in Ireland. The ETR there is calculated at 12.5%. The group owes a 2.5% top-up on those profits. If Ireland has a qualified QDMTT on their books, Ireland just takes that 2.5% themselves, right?
That is correct. And this is going to be the dominant outcome for filers in 2026 and beyond. Most historically low-tax jurisdictions like Ireland, the UK, the Netherlands, and Germany have rapidly enacted qualified QDMTTs precisely so they can collect their own top-up revenue rather than ceding that money to another country.
Right. Why give the money away?
Exactly. If the QDMTT applies, the other 2 mechanisms see a residual of 0. The water is caught entirely in the first bucket.
But it's a waterfall. What if that first bucket has a hole in it? What if the source country hasn't enacted a qualified QDMTT? Say the subsidiary is in a pure tax haven that refuses to update its laws. The water spills over to the second bucket, the IIR.
IIR is the income inclusion rule. If the source country doesn't collect the tax, the right to collect flows upward through the corporate ownership chain to the ultimate parent entity's jurisdiction.
Up the ladder.
Exactly. So if a parent company headquartered in France has a subsidiary in a zero-tax haven that lacks a QDMTT, France gets to step in and collect the top-up tax on those haven profits.
Provided France's IIR is qualified by the OECD.
Exactly. And most of the EU, the UK, Canada, Australia, and Japan have qualified IIRs. But there is a massive, incredibly complex caveat here that OrbaOS strictly enforces regarding the United States.
Oh.
Currently, the U.S. GILTA regime, the Global Intangible Low-Taxed Income Rules, which is the U.S. version of the minimum tax, is not yet recognized by the OECD as a fully qualified IIR.
Wait, so if I'm a U.S. parent company and my subsidiary in a tax haven owes top-up tax, the U.S. government can't use the IIR mechanism to collect it under the OECD rule.
It creates a structural routing problem. The U.S. parent is skipped over in the OECD logic.
Oh, wow.
Which brings us to the final bucket, the backstop, the splash at the bottom of the waterfall, the UTPR.
The undertaxed profits rule. If the source country didn't collect via QDMTT and the parent country isn't qualified to collect via IIR, the top-up tax doesn't just evaporate, it gets gathered up and split.
Yeah.
How does that split work?
The residual tax is allocated across all the other jurisdictions where the multinational group operates and has physical substance. It's not a free-for-all. It's a specific, hard-coded formula defined in Article 2.6.2.
Okay, what's the formula?
The tax is allocated based on a ratio. Half is based on the jurisdiction's share of the group's total payroll, and half is based on its share of total tangible assets.
Let me make sure I have this right. A U.S. parent company has a subsidiary in a zero-tax haven. The haven has no QDMTT. The U.S. has no qualified IIR. The tax falls to the UTPR.
Right.
The company also has a massive manufacturing plant in Germany with thousands of workers and heavy machinery. Germany has a qualified UTPR. Are you saying Germany gets a significant slice of that leftover top-up tax, even though the untaxed profits were generated in a haven halfway across the world by a U.S. company?
That is exactly how the math works.
That is wild.
And here is where the OrbaOS admissibility doctrine proves its worth yet again. A multinational filing this tax return cannot just hope a country has a qualified QDMTT or make a judgment call on how to route the tax to minimize their exposure or avoid angering a specific tax authority.
Because the routing logic isn't a suggestion.
The routing logic in OrbaOS is completely deterministic. It is hard-coded to the OECD Administrative Guidance Central Record.
Okay.
The system knows exactly which jurisdictions have achieved qualified status for QDMTT, IIR, and UTPR based on published OECD facts. The engine encodes the routing as a deterministic pipeline. When the calculation runs, the output route enumerates exactly which mechanism collected which source, tied cryptographically to that central record parameter set.
It is an unarguable mathematical proof of compliance with a geopolitical treaty.
Yes.
It's breathtaking how they've taken this infinitely complex politically charged tax treaty and reduced it to a cryptographic certainty. But listening to this, if I am a CRO or a group tax director, a system this strict, this unforgiving, sounds absolutely terrifying to implement.
It would be, yeah.
You are telling me that if one analyst echoes a hash wrong, or one local accountant changes a spreadsheet cell without recording it, the entire multi-billion-dollar calculation halts. How does a massive, slow-moving institution adopt this kind of cryptographic strictness without totally breaking their legacy reporting workflows overnight? You can't just flip a switch on a massive bank.
That is the practical genius of the OrbaOS deployment model. They recognize that you cannot demand cryptographic perfection on day one. It would cause organizational shock.
Total mutiny.
Right. So they built an adoption path controlled by a single environment variable called admissibility mode. It governs the strictness of the entire platform, and it has 3 distinct states: warn, gate, and block.
Let's break these down, because this is the bridge between the messy reality of today and the cryptographic ideal of tomorrow. Mode 1 is warn. How does warn mode function?
Warn is the onboarding posture. When the system is in warn mode, the admissibility doctrine is watching everything, but it isn't stopping the traffic. If a user uploads data with a provenance gap, say they bypassed the hash echo step entirely, or they mutated a cell after commit, the system proceeds with the calculation. It generates the export. It preserves the legacy upload paths so the daily business doesn't grind to a halt.
But it's not ignoring the error, right?
No, crucially, it silently persists an inadmissibility event in the background. It logs exactly where the provenance broke, who broke it, what system they were using, and when.
So what does this all mean for the audit team?
It means that refusals become queryable data. Instead of an auditor finding a massive mistake a year later and everyone panicking to figure out what happened, the audit team can query the system at the end of the quarter and say, show me every refused computational state.
Oh, I love that.
They can see exactly which trading desks or which corporate subsidiaries are struggling with the new data hygiene standards.
It turns errors from hidden landmines into a dashboard of teachable moments. You can train the specific teams that are failing before you enforce the strict rules. Okay, so a firm spends a few months in warn mode, they clean up their data pipelines, they retrain their staff, and they're ready to step up. Mode 2 is gate.
Gate is the operating posture for a maturing organization. In gate mode, the training wheels come off. If the system detects a provenance gap, it refuses the calculation. It throws an HTTP 423 locked error. The pipeline stops.
Okay, that sounds like the organizational paralysis we were worried about.
Yeah.
If an analyst makes a mistake, the whole calculation halts.
But there is a release valve built into gate mode. To proceed, the system requires a 4-eyes override. A single-use overwrite token must be presented to the system.
Okay.
And the rules for this token are incredibly strict to prevent abuse. It is scoped exactly to the specific operation, the specific portfolio or filing group, and the specific reason code for the failure. Furthermore, it expires in 5 minutes.
You can't just leave a master override key lying around on a sticky note.
Precisely. And here's the masterstroke of the governance design. The token must be consumed by a different actor than the one who issued it.
So the analysts who triggered the error cannot override it themselves.
They cannot. They must physically or digitally go to a supervisor, explain exactly why the provenance gap occurred, and the supervisor must issue the token.
Oh, that's smart.
This forces acknowledgement and pairs the actors in the permanent audit log. Every single deviation from cryptographic perfection becomes a paired, deliberate, highly scrutinized audit event.
That is brilliant change management. You enforce the rule, but you allow exceptions, provided the exception is highly visible and cryptographically logged. But the ultimate destination, the promised land of this doctrine, is mode 3, block.
Block is the destination state. When a firm switches the environment variable to block mode, there are no exceptions.
Period. Yeah.
A provenance gap results in an HTTP 409 conflict. The system fails closed. There's no override path. Even a senior supervisor with a token gets rejected. In block mode, every single figure that ships out of that system, every capital requirement, every GloBE XML filing is anchored to a mathematically verified route. The admissibility doctrine is fully immutably enforced.
That is the boardroom nightmare solved.
Yeah.
When you are operating in block mode and the regulator says, prove that number, you don't even blink. You know the number is perfect. But this brings us to a really practical question of deployment. Where does all this data live?
That's a good question.
If I'm a massive global bank, I am absolutely not uploading my highly confidential trading book sensitivities to some RegTech startup's cloud server. The security risk is too high.
And they shouldn't. OrbaOS explicitly states they are institutional infrastructure, not a self-serve SaaS product. The platform is self-hosted by default.
Okay, so how is it delivered?
The entire stack, the Postgres database, the Fast API backend, the React frontend, comes down as a Docker Compose package. It is designed to run entirely within the client's own environment on their own secure network, behind their own firewalls.
So the core data never leaves the building.
Yeah. Crucially, no. The trades, the sensitivities, the constituent entity financials never cross the open internet to a vendor. And what's fascinating from an architectural standpoint is how efficient it is.
How so?
Both calculators, FRTB and GloBE, are essentially distinct front ends sitting on top of the exact same shared Postgres database and admissibility governance substrate. The business tables are different, portfolios for FRTB, filing groups for GloBE, but the fundamental tables tracking the Merkle nodes, the edges, and the inadmissibility events are shared.
Oh, that's clean.
It's one unified governance layer for the institution's most critical regulatory numbers.
This all sounds incredible, but how do they actually sell a paradigm shift like this? Because you can't exactly offer a 14-day free trial of a cryptographic infrastructure overhaul with a sign up with Google button on a website.
They don't try to. The sales motion is highly controlled and highly technical. It starts with a conversation to ensure the prospect actually understands the difference between institutional infrastructure and a simple spreadsheet alternative.
Right.
If there's a fit, OrbaOS spins up what they call a private demo tenant.
Let's break this down. What is the private demo tenant? Because the documentation is very clear. This is not a freemium playground for people to poke around in.
It is a highly choreographed experiential proof of the doctrine. It's a dedicated, isolated environment scoped specifically for the prospect. They don't just throw you in with generic dummy data.
Okay.
The OrbaOS team preloads the tenant with synthetic data shaped exactly like the prospect's real world. If it's a bank, the synthetic data mirrors their actual trading desks and asset classes. If it's a multinational, it mirrors their specific jurisdictional footprint and ownership chains.
So when the tax director logs in, they are interacting with data that feels structurally identical to their own messy reality.
That's the goal. And then you go through a guided 45-minute exercise. You don't just watch a slide deck or a pre-recorded video. You actively execute the doctrine.
You do the work.
You upload a CSV file. You watch the system parse it and demand the hash echo. You commit the hash. You run the calculation and receive the Merkle root.
And then, the best part, the falsification test.
The falsification test is where the abstract becomes real. You deliberately mutate one cell in that CSV and re-upload it. And you watch the stateless verifier catch you instantly, flagging the exact broken node in the Merkle DAG.
That's got to be a light bulb moment for them.
It is. Then you experience the governance toggle. You flip the system from warn to gate, trigger an intentional error, and are forced to issue and consume a paired actor override token to proceed.
It is tactile proof that the math and the governance actually work exactly as promised, and then I assume the tenant just exists for them to play with forever.
No, it is strictly time-boxed. It automatically tears itself down after the engagement window closes, typically 14 days.
Okay.
It is purely designed to let the prospect walk the doctrine end-to-end on their own laptop, prove to themselves that the offline verification works, and understand exactly how their relationship with regulatory compliance is about to change. Only after that experiential proof does the conversation shift to downloading the production tarballs and deploying on their own infrastructure.
It's a completely different way of thinking about software adoption. You aren't buying a tool, you're adopting a mathematical doctrine. Okay, we have covered an immense amount of ground today. We started with the sheer terror of untraceable spreadsheets breaking multi-billion-dollar capital and tax programs. We unpacked the admissibility doctrine, admitted before calculated, the elegance of the Merkle DAG, and the ruthless efficiency of the stateless verifier catching those 5 failure modes.
We covered a lot.
We saw how this applies to the dizzying math of FRTB market risk and the labyrinthine waterfall routing of the global minimum tax. And we explored how an institution can actually transition to this reality using warn, gate, and block.
The core value proposition here is a paradigm shift. We are moving away from an era of trust me spreadsheets, manual reconciliations, and opaque models. We are entering an era of mathematically replayable, cryptographically secure chains of evidence for the highest stakes regulatory reporting in the world.
It fundamentally takes the anxiety out of the boardroom. But I want to leave you, the listener, with something to mull over, something beyond just the mechanics of this one platform. What is the long-term implication of this technology?
If we look at the trajectory, this raises a deeply provocative question. If cryptographic lineage can make multi-billion-dollar market risk figures and global minimum tax routing mathematically undeniable today, how long until regulators realize they no longer have to accept the ambiguity of the past? How long until regulators stop accepting traditional spreadsheets entirely? What happens to the entire global financial industry when admitted before calculated stops being a competitive advantage for early adopters and becomes the absolute legal baseline for every single corporate filing?
That is a staggering thought. The end of the spreadsheet era, replaced by cryptographic truth. And it brings us right back to that quiet, tense boardroom we started in. Imagine that auditor sliding the paper across the desk, pointing to the massive number and asking, "Prove that number." But this time, you don't panic. You don't hand them a folder of messy exports. You just smile, hand them a flash drive with a JSON lineage file and a single Python script and say, "The math proves itself." Thank you for joining us on this deep dive. Take a hard look at the integrity of your own data pipelines, and we'll see you next time.